with, and I have counted the number of phases, which is not that difficult in this case. It's 7, and if you also include the I and J options, so miscibility gaps, 13 phases would be included in the Gibbs minimization itself. Okay, now if you look into the slick phase, you will see that there are these 5 different end members. So in terms of, and now I again want to include the terminology, end member. Each of these things that you see here on the slide is an end member of this solution model. And I still can't move on. Which is because I have a lot of animations. I always love animations, but that is sometimes a curse. Now the wonderful information increase on the slide. Also on the slide, we now counted to 5 as in terms of the number of end members in the slick phase. And if you continue this, you can also look at the BCC phase that has 2 different end members, an iron end member, an oxygen end member. And then the MEO phase has 3 different end members. This becomes a bit more complicated, with the first end member being a stoichiometric iron monoxide. The second end member being an iron 3 plus O2 minus with a 1-to-1 stoichiometry. So this is an FeO with a 1 electron positive charge. And the third end member is just oxygen with a double negative charge. I don't want to go into details on the electron constraint. Again, you see constraint, but I had to skip that. Okay, good. If we do the counting for all of the 7 phases, we end up with 47 different end members in total. Good. Now, I only had one internal energy versus composition curve in my earlier talk. That is a pity. I need a Gibbs energy versus composition curve, otherwise I can't sleep tonight. Here you see diagram Gibbs energy of iron versus oxygen. So on the x-axis is the composition axis, going from the pure iron to the oxygen. And let's go through the gas phase. The gas phase, as you can see here, has these 5 different end members again, and we can place them here in this diagram. So you can look up into the database compound module, you can look up the Gibbs energy of each of these end members, and you find the numbers, or you can plot the numbers as I've done here schematically. Yeah? Okay, well, you see there's the oxygen O2, which is of course the stable oxygen molecule. There's the ozone, and there's the atomic oxygen in the gas phase. There's an FeO molecule in the gas phase, and there's the pure iron in the gas phase. If you think about what is the Gibbs energy surface essentially, or the Gibbs energy that you can define with these 5 different species, it is this blue area. If you have a combination of all of them, you will have a Gibbs energy that will probably be here at the lower bar. If you have only Fe gas and FeO gas, you will probably have a Gibbs energy that would follow here. It is slightly a slight deviation from a linear curve because of the minus T delta S mix ideal contribution. Yeah? Okay, we care about Gibbs energy minimization, so of course we don't care about the whole plane that you can have with the Gibbs energy model, but we only care about this line, right? Good. Okay, good. Then let's forget about all of the details of the end members. This is our Gibbs energy model of an equilibrated gas phase in the iron-oxygen system. Now we can add also the BCC phase. As I said before, the BCC phase is modeled from pure iron to pure oxygen, left to right. As you can imagine, pure BCC oxygen is really, really, really unstable, which is why this curve is hitting up here and not closer to the stable O2 molecule, which is down here. Yeah? Good. We can also add, for example, the MEO phase, which will then be somewhere down here. That's our Gibbs energy model of the Wüstheit phase. It is going from the 1-to-1 stoichiometry here to actually to a 2-to-3 stoichiometry that you can get by charge balancing the 2 lower end members here. And then we can also add the other 2 solution phases, the Spinel phase, which is around the Fe3O4 composition range, and the hematite, which is at the Fe2O3 composition, and that's actually modeled only as a point compound, and this is why I've only put this here as 1 point. Okay, you can also see that I used a broader Gibbs energy model for to depict the MEO compared to the spinel, because the MEO has this of stoichiometry. The Wüstheit can have can accommodate quite a number of vacancies, can change the composition. All right. Now, a short notation change. I have earlier I used the SCS and end member, and I just want to replace this and also phases written out, because I will now put a few equations in. I just want to introduce the notation. SCS stands for system components, phi stands for phases, and NEM in phi are the end members in a phase. Okay? Good. Other than that, there was no change here, just notation change. Good. Talking about notation, for those who are sitting in front and probably the online audience, you at least can see that I put here the number. So a capital N stands for a number of something, a small n stands for an amount of something, and a y here stands for a fraction of something. Good. Our goal is to find the equilibrium Gibbs energy as a function of temperature, pressure, and amount, so small n, of our system components. Good. How do we do this? So let's take a case here where we have some composition. So this is our NSCS vector, essentially. In this case, it's just one number, because it is a fraction as it is depicted here. And we want to know what is the minimum Gibbs energy for this composition. And in order to calculate that number, we have to go through a minimization problem where we are changing in the Gibbs energy minimizer the amount of the different phases phi. So phi here going from the gas to BCC, MEO, spinel, and so on and so forth. And also the fraction for each phase, the fraction of the different end member species, or the different end members. So what does this mean? Considering the fraction of end members in a phase, let's say here the gas phase, this is exactly what I talked about earlier. This is the area of Gibbs energies that you can describe using the species in the gas phase, and we want to only look at the minimum of this curve. Yeah? Then concerning the other part, the n phi, we care about exactly this curve down here, where we have some amount of BCC, some amount of MEO, and what we do not care about is this one, or that one, or that one, or that one, because all of them have a Gibbs energy that you can read here, which is higher than what you have down here, right? But the solver is going through all of them, and in order to find finally this one solution. Yeah? Wonderful. Now, what I'm describing here with this minimization, it was so trivial, right? What I have described is actually the constraint. We have a constraint that is active when we go through the amounts of phases phi and the fraction of end members in these phases phi. And this is connected through this mass balance constraint with the amount of system components that we have. Yeah? We can't combine 1 mole of oxygen with 1 mole of Fe2O3 if our system composition has only 20% of oxygen. Yeah? Good. So here is already the feared word, constraint. And it's super simple, right? It's just mass balance. Good. How is this, how can you visualize the mass balance constraint? In order to visualize it, the stoichiometric matrix is a super nice concept. And I want you to fully understand that the stoichiometry matrix is super easy and trivial. So if you have we have here in the first column, we have a phase end member. So the gas has the 5 different end members here. And then we have here in the second and third column, the stoichiometry of this end member with respect to iron or with respect to oxygen. I hope there's no question concerning how I have filled in this table, right? It's trivial. Good. And this is also what I talked about earlier. These are the species or the end members I have introduced earlier. All of that you know. And then what are our constraints that we apply during the Gibbs energy minimization that Gunnar so nicely implemented many, many years ago already, which is simply that the amount of iron in total must be equal to the sum over all of the amounts of the phase amounts phi, times the stoichiometry matrix, so this stoichiometric coefficient with respect to iron, times the fraction of that end member. Yeah? So this is all there is in terms of mass balance. That's it. Good. Once you have this, now you have understood how to solve this problem. I have now simply added here the information that we have 0.8 mole of iron, 0.2 mole of oxygen. I was too lazy to write mole. Sorry for that. And I have now introduced a new constraint. I've introduced the constraint that the system consists only of BCC iron and a spinel Fe3O4. Okay, so what I'm looking for is this new Gibbs energy tangent line that is down here, ignoring that there is an MEO phase, but only taking into account the spinel and the BCC phase. And we can calculate that. Probably many of you have already calculated such a system by the phase selection or the species selection in FactSage. Yeah? So the only thing you have to do is to cross out all of the phases that you don't want to consider. If you know your system consists only of BCC and the spinel phase, you just don't select all of the other phases, you unselect them, and you're able to calculate the Gibbs energy for exactly that system, which is exactly here, right? Okay. Sometimes you want to do something else, which is you might want to know what is the driving force for the MEO formation. I have said earlier, the driving forces are super fundamental in all process models, both for the transport and for the reaction kinetics. So how do you calculate the driving force? Well, the only change you have to do is that you do not eliminate the MEO completely, but you set it to dormant. So you use this exclamation mark option in Equilib. And then what you get is an activity for this phase, and that activity you can trivially recalculate into the Gibbs energy difference of this point compared to the green dotted point there compared to the black line. Okay. Good. Now let's become a bit more fancy. Now we say this system transforms to equilibrium, but there is a kinetic constraint that leads to 0.01 mole of spinel Fe3O4 to remain because of some kinetic limitation. Now this kinetic limitation is again a constraint, so we can apply this constraint in here. How? Well, we introduce this QA and we link it to the spinel. What do we do if we do this? Because we've talked at the users meeting before about the QA already quite a number of times, but I really want to describe it carefully. We add a new column to the stoichiometry matrix, which is our constraint, the fact that 0.01 mole of spinel will always maintain, is expressed through this new system component. And now we add 0.01 mole of QA to the system, and that means we're not anymore in a binary FEO system, but now we're in a ternary system. So we have a third or a new dimension in this diagram. We had the x-axis for the iron to oxygen ratio, we had the Gibbs energy on the y-axis, and now we have for the in-plane axis, we have the amount of QA in the system. We are now in a ternary system, and this is our composition. Okay, wonderful. What else do we have to do? This was our Gibbs energy, or these have been our Gibbs energy curves, which lie in the FEO plane. They lie in the plane where you don't have any QA. Yeah? And now what we have to do is we move the spinel phase from this FEO plane into a plane that is between FEQA and OQA. Yeah? So please watch the shadow of the spinel phase that is down here. Currently it's on the FEO plane, and now it's moving into the third dimension. Yeah? Now this spinel phase is not part of the FEO system anymore. It is only part of the FEO-QA system. And that means that now if we do a Gibbs energy minimization, we will find a tangent plane, not a tangent line anymore, but a tangent plane connecting the BCC, the MEO, and the spinel QA phase. Yeah, and you see here, you can then apply the lever rule using this, or in this triangular plane here. Yeah? And this is super nice, because very often there are these constraints. I talked earlier about this diagram, about the basins we have that we call phases. And I said, yeah, okay, and then there can be phase transformations, for example, the Baben transformation, but very often these are constrained, these phase transformations are constrained because this energy barrier that's between them simply is too high. The atoms do not manage to overcome that barrier to come into the more stable state. And in order to treat this, we can use the constraints. And we have prepared a couple of presentations for today. The next presentation will be on using constraints in order to describe constrained equilibria in condensed phases by Philip. Then Anna will talk about kinetic limitations in the gas phase, using constraints to describe the methanol synthesis. 2 years ago we described the ammonia synthesis. This is like a toy system that we're going through. Every time we are bored, we go to some synthesis in the gas phase and we check whether we can model this, and actually, yes, it's working quite nicely, and reduces the number of fitting parameters. Okay, while Philip will talk about eliminating phases and also setting phases dormant, Anna will eliminate phases and she will also introduce QA as an extra constraint. Then Joao will later talk about using electrolysis to drive systems away from equilibrium. So you're using the electrical potential, and there, because simply we like to do this, we don't call this QA anymore, but it's just QE for an electron. But that is used in the electrolysis case. Joao will also eliminate a couple of phase constituents. And then after that, I will talk again because Alex is unfortunately not here, and I will tell you how we can use constraints to for an explicit treatment of microstructural defects, in that case grain boundaries that are linked to a constraint. Good. And if you want to know more, there are 2 publications that we wrote in the last years, where we explain all of the concepts, how to use them rather conveniently, which I would suggest as further reading. And with this, I hand over. I guess I can hand over directly, unless there's a super urgent question.
No, I think we should ask questions in these separate talks. So if you have a question for Moritz, you have to wait until the 4th one.
Okay.
But the others are also capable of answering. So with this,
Perfect.
We can maybe continue with Philip.
Yeah.